Hello and welcome to our data types and memory course. Alright, so when you interact with objects in the real world, you usually see strings, numbers, cars, keyboards, monitors, windows, mice. Uh, well, hopefully computer mice, not real mice. um, you interact with these types and you kind of implicitly figure out what they are and you know how to interact with them and you know what to do with them. You know what the numbers 418 mean. If someone's talking to you about that, you usually have some sort of context. Well, in computers, uh, computers need to be told that context specifically. So in the computer world, specifically around, I guess in C++, that's what we're going to be looking at, there's these specific data types. But the goal is that we need to be able to tell our programs how to interact with the types that we want to work with. So in C++, we're going to get the bool type, which is going to give you a true or false, two possible values, true or false. There's the char type, which is a single character. It's one of the ASCII table values. There's the int type, which is going to give you positive and negative integers. There's floats, which are positive and negative rational numbers. Then there's a double, which gives you positive and negative rational numbers again. But this is going to be more precise, and we'll go over the differences and what that actually means here in a few minutes. Then there's also a special type called void, which really means no data type. I want to just point this out to you because you're going to be seeing it when we move into functions and talk about return types. But if you see void, just know that, oh, that just doesn't really mean anything. Alright, so those are the types that you're going to see in C++. Those are the built-in types, and those are the ways that we're going to interact with the basic primitive data in the C++ world. Alright, so now there's storing data. We have different ways to store data, different mediums. There's hard drives, there's RAM, and there are DVDs. Each of these three pieces of technology are significantly different than one another. Hard drives have spindles, they have magnetic disks that you write data to. RAM is essentially flash memory. It's electronic bits being stored on there. DVDs are optical mediums. They basically have pits burned into the disk layer, and then the laser bounces off at different frequencies. So while each of these are significantly different in their physical medium and their actual implementation on transferring data, the way in which that data is stored is the same. It's all in binary format. And so binary is essentially a string of zeros and ones that the computer can interpret and turn into data, or instructions or operations for the computer to work. When we're looking at a binary stream and we look at a specific instance of one of those values within the stream, that's called a bit. Now when we actually move up and look at multiple bits at a single time, specifically when we look at 8 bits, then we're looking at a byte. So I just want to go over this terminology so that when we start talking about our data types again, we'll have some information and some context on what these actually look like. So 8 bits is 1 byte. And so we talk about those in bytes because we don't always want to say 8 bits when we can just say 1 byte. It's easier, especially when we start talking about a large number of bits. Alright, so we have these data types and we have this kind of high-level understanding of how data is actually stored on our different devices. So let's take a look at what our data types look like in memory. So we have the Boolean. The Boolean value, or if you remember, the Boolean only takes 2 values, true or false. So really that could be stored in 1 bit. However, since the way computers work, it's actually faster to store and not to store, to move around and manipulate 8 bits of data in the smallest chunk as opposed to 1 bit. So because of that, in C++, the Boolean value is actually going to be 8 bits long, but you still only use the values 0 and 1. So that's the only kind of weird data type that we're going to be looking at today, but just so you know, a Boolean only needs 1 bit, but it's stored in 8 bits just for speed purposes. Then we have the char, which is 8 bits long. 8 bits in binary allows you to store 256 possible values, and that's the way binary works, and we'll be talking about how binary works in our next video. But the char stores one of the values in the ASCII table. If you don't know what the ASCII table is, just go look it up. But essentially, it's the table of printable characters that make up the keys on your keyboard and most of the English type characters. So you won't see any Japanese or script type characters in the ASCII table. The next we have the integer, which is normally 32 bits. It's 4 bytes long, and it has the value ranges between -2 to the 31st power all the way up to 2 to the 31st minus 1. And so it's minus 1 on the end because we need a placeholder for 0. So if we were to go 2 to the 31st in the negative direction and then 2 to the 31st in the positive direction, we'd get our full value of 2 to the 32nd, but then we would be missing 0. So we need to truncate one ends. It so happens to be that truncating the upper end is more convenient, so we take off the 1 from the upper end and replace that with 0 so that we can have a continuous set of values between -2 to the 31st all the way up to 2 to the 31st minus 1. So I said most of the time. And C++ is kind of funny in this way, in that your value types aren't actually necessarily a given size. And so they depend on two things. There's the computer architecture that you're working on, and there's also the compiler that you're working with. So when we think about computer architecture, we typically think 32-bit, 64-bit. Those are typical desktop architectures that we see now. But there's also other computers that you could be working on. You could be working on some mobile devices or some gaming devices, and they may have a different bitness to their architecture. And so that will sometimes have an impact on the size of integer values and floats and doubles. There's also the compiler. So just because you're on a 32-bit system or that you're on a 64-bit system doesn't mean that your integers will necessarily be 32 bits. Now this is the case now, but back 10 years ago, maybe 5-10 years ago, just because you're on a 32-bit system, you might actually have 16-bit integers. So kind of like that today, just because you're on a 64-bit machine doesn't mean you'll actually have 32-bit, or doesn't mean you'll actually have 64-bit integers. You may actually have 32-bit integers. And in the most case, that's actually going to be true. So the important thing here to note is that you need to check with your compiler and the computer that you're on to ensure the size if you're going to be approaching the bounds of either one of those, or if you're going to be doing anything that makes assumptions on the size of those types. All right, so that's the integer. It's 32 bits, 4 bytes. For the purpose of this class, I don't think there'll be anybody out there that will have I don't think there'll be anybody that runs into something different than that. The next is the float value, which allows you to store rational numbers. It gives you 32 bits of data to do that. And so that's going to give you roughly 7 digits of precision. I know that doesn't really make sense, but we're not going to really be going too much into the implementation of floating point numbers. But really, I just want you to take away that a floating point value gives you a larger range than your integers, but you lose precision in doing so. The double is going to give you 64 bits, so you're going to get twice as much space, so you're going to get a little more than twice as much precision. So you're going to get a much larger range of numbers that you can actually use with the double. It's going to take 15. You get 15 digits of precision, uh, but it takes 64 bits of memory. So double takes twice as much memory, twice as much precision. So with that, that's just going to wrap up this video. In the next video, we'll go ahead and talk about how integers are actually stored in memory, how we can convert binary to decimal, and get all that fun stuff working. Thanks.